Hello! Hello! What is up, chat? How's it going today? Now we're live. We're live on YouTube. We're live on Twitch. We're live on stream.bfa.lk, my favorite streaming site. Everyone put your poggers in the air for stream.bfa.lk. Welcome to the stream. Today we're going to be banging out some code. We're going to be looking into different things that we can analyze. We're going to be modeling the whole world using the magical powers of fuzzing and computers. How does that sound, chat? Is that not hype, bim, skibbity? Is that not what you want? Because that's what we're going to do today. All right. So I've been rebuilding my lathe, for a pretty long time now, like 6 months. And I really want to get my lathe up and running so I can use it, but I don't really know my next best steps for improving the lathe. And I'm pretty convinced that I am not converging to accuracy right now. Just due to the way I'm measuring things, it's pretty hard to measure. I don't have like a straight edge or a parallel that is as long as the lathe. So I have to basically try to approximate where things actually are on the lathe through the magical process of like hinging a smaller piece of straight edge on the lathe beds and trying to take measurements from that. Unfortunately, that's really hard and very subjective. It's kind of like feeling out where sticky spots are. And it's really hard to feel that out because there might be a spot of oil on there. There might be some grease on there, some debris, some leftover chips, a raised bump from a scratch. And obviously you try and clean it, you try and wipe all that down, but inevitably that is part of your measurements, and it's going to lead to you making some mistakes. So what I've been trying to do is I've been trying to model my lathe bed purely with my level. And my level allows me to theoretically measure things like twist and all sorts of differences between the beds that I can't do with a traditional just straight edge. At least, you know, a very simple straight edge. So I'm going to talk a little bit about how I've taken a bunch of measurements for my lathe. I'm going to show you kind of what I've already written offline here, and the issues I have with it and the improvements I need to make. And then from there, we'll try and do some of those improvements. So, how does that sound? That sound fun? Raise your poggers if that sounds fun. Okay. Everyone's poggers are raised. Okay, that's good. So, basically, what I should show you is the measurements that I've taken. Now, unfortunately, I don't have a great way of putting, like, photos up on stream? How would I do that? What's the best way for me to do that? Okay, let's see if I can... Let me see. I'll just send things to myself. So I think I have a decent amount of photos of my actual setup on the lathe. Let me see. Let me see. Start a conversation. Okay, let me go and... Actually, I'll post them to my Discord. There we go. I'll go to my Discord. I'll post them there. So then people can look at them there if they want to stare at them longer. And then I have to find these photos. Hey, I was very smart to take a bunch of photos. Like a very smart person that I am. Because I'm very smart, chat. Okay? Cool. Okay. Bam. There's a bunch of photos. And we can go take a look at what they look like. All right? So, so in Discord, if you're not in my Discord, you're missing out. You should come hang out. It's a cool group of nerds and losers. Hope you're doing well. I'm doing fantastic. Okay, so here is a... Dude, why do photos uploaded from iPhone Discord look so fucking... like, why can't I zoom in on this? Why is that max zoom? If I go to open in browser, then I get the full photo. But, like, why is the preview? Is it like that for Android uploads too? Oh, it's terrible. Anyways, okay, so here is a picture of my lathe bed. Can everyone see this? Is everyone being a good boy? Okay. So this is the lathe bed. So you're looking down the lathe. I don't know why your mouse cursor doesn't show up on a photo. That's great. Is it only in full screen mode? No, just photos in general, your mouse cursor doesn't show up. That's so weird. Why? Why? That's so strange. Anyways, so like here's the operating panel. This is like where I would actually be standing. And thus the edge that's kind of closer to us here, which is near this black stick, that's a scraper, that is kind of the front edge. You can see the serial number and the lettering there that is in the orientation that you'd read. And then we have the back edge, obviously on the back edge on the other side. Man, it would be really nice if my cursor worked. Why is that? That's so strange. Okay. So anyways, what I've done is I've gone through and I've marked every, I think, 40 millimeters, and I've gone and, every 40 millimeters I've gone and I've drawn a line on the lathe, right? So, do I even have CRUD installed? No. I have GIMP. Oh, that's so much better. Oh, yeah. Okay. So, okay. So this is the lathe. And this is actually kind of important for you to understand what we're doing. Because someone could bring up potential flaws or issues or improvements that could be made. Now, obviously, the whole point of this is that we can model something with reasonable measurements for us to make, right? So, this isn't about, theoretically, there's a facility in Germany that has a machine that could image this, and that's how you do this, right? Like, this is about what can we do with literally what I have right now. I'm not going to spend $500,000 to rebuild a $10,000 lathe. Okay? Okay, chat? So, all you nitpickers, get out. All right. Anyways. So, this is the front side of the lathe here. This is where the operator would stand and kind of do lathing operations. So, we're looking kind of down the bed. So, towards here, this is where the spindle actually would be, and where you would machine your parts, right? Okay, so what I'm trying to do right now, and the only thing that I'm doing, I'm starting and making the reference surface for the lathe that I'm going to use for all other things. So this is going to be the true surface that I will make as precise as possible, and then everything else on the lathe will be derived with respect to this. And that is these flat surfaces here. So these long flat surfaces, they're about 1 inch wide. I think they're intended to be exactly 1 inch wide. And they go down the entire bed. So this one goes to here, and the other one goes a little off the photo here, just a smidge beyond. So this one actually runs a little bit further, and you can see that this inverted V here goes a little bit further. And this is actually, these are the 4 bearing points of the headstock, which basically determines where the spindle rides in its axis with respect to the lathe. So these points will be extremely critically scraped in, but what we're just not even thinking about the head, but just kind of for some reference of where everything's at on the lathe. Okay, so what I want to do is basically get these surfaces, these flat surfaces, I want to get these surfaces completely flat and in the same plane as each other. Which means that I want, effectively, there to be a surface, a plane, of which exists in 3-dimensional space, that both of these flat surfaces, all points are, like, directly intersecting that plane. Now, obviously, that's unrealistic. Like, in reality, we're going to talk about, like, basically 1 to 5 micron valleys and grooves and divots and dents and scrapes and bumps and all sorts of things and hills and biases and, like, everything is warped and bent and when you look at a low enough scale. So the scale that I'm working on building this lathe up to exceeds that of, like, effectively temperature. Like, different heat differences will affect the readings I get from day to day. So I'm trying to get the bed of this lathe ideally within, like, 2 or 3 micron. In reality, I know 5 should definitely be possible. I don't know if we can get down to, like, 2 or 3, but it might be possible. So what I'm trying to do is I'm trying to figure out how far can I go. Now, obviously, there's an exponential effort there, so it's more about, like, how far am I willing to go. Eventually, I'll see, hopefully, some diminishing returns or lose the ability to measure, at which point that's when I'm done. So what I'm trying to do now is gain visibility into what these beds look like right now. So these ways, in my opinion, and when I say in my opinion, I mean over thousands of measurements and my internal brain mapping of the lathe, I think these are basically flat and within the same plane within maybe 25 or 30 micron right now. It could be up to 50, but I think somewhere between, like, 25 and 50 micron is roughly how much these deviate in waviness, in curvature, in slopes falling off on the edges. And those are the sorts of things that I want to try and figure out if I know. So why do you need such high flatness in these rails? These are basically what determines where your tool is, and your tool is digging into your part and cutting the shape into the part, right? So effectively, this is what if I were to have a bump on this surface like that, and I were making a cylinder, a long cylinder, that long cylinder would then have an hourglass shape, right? Now, in reality, we're talking where this hourglass shape is, like, maybe 10 micron, right? In which case, most machining in the world is probably done to a tolerance of, like, 50 to 100 micron is probably completely fine. Like, literally, parts are going to be perfect and fine. There are some things that get down into like the sub 20 micron range, and that's going to be like critical bearing journals and mating surfaces in things like engines and other things. For reference of kind of the for people who aren't necessarily into machining or into just physical things, 10 micron would be considered quite good for a lathe. Like if you throw a part in there and you run it down a relatively long cylinder that's like a decent, maybe half or more than half of your bed, and you get like less than 10 micron of like dips in there, that would be fantastic, right? That is actually really, really, really good. The Monarch 10EE that I have, I think, had its ways, they were down to like 2/10, which is 2/10,000ths of an inch, which is like 5 micron. I think from the factory, that was the original specification. Keep in mind, there's all sorts of components that also need to be square and parallel with each other for that whole system to stack up together, right? And obviously I'm going to be going through that whole system, but I'm starting at the very base, right? This is the foundation. This is what everything on the lathe sits on. This is where the moving carriage sits. This is also where the headstock sits, which holds the part. So this is literally the reference surface. Now, in reality, the bearing points of the headstock are these 4 corners. So from the factory, they actually didn't care about the finish of the rails behind like this line. They effectively just worried about these 4 contact points with the headstock. But what I'm trying to do is I'm just trying to make everything flat, square, parallel in the same plane, such that in the future, I don't have to think about like, oh, was this supposed to be a little bit lower? Was this like a dip here? Should I restore the dip because does the headstock expect that? From my viewpoint is that when 30 years from now, someone tears down this machine and is trying to figure out like, you know, what needs to be repaired or fixed, that if they lay a straight edge across it, it's pretty apparent that the whole thing was made flat, in which case restoring the whole thing to being flat is the correct thing to do. Basically, it cuts out some random wishy-washy, like, only selective areas are intolerance. That is the correct way. Only worrying about the things that actually bear is the correct way to do parts, right? You shouldn't spend time improving something that literally is not relevant to the equation of the precision of the machine. It's just literally a waste of time. However, I view it convenient for a reference because it means it's just easier to set up gauges and indicators and measure things. Also, the surfaces that don't contact things give you a historical reference point as to what was flat. So maybe the next owner might not know that, but I know that if I go and restore this machine in 10 years or something like that, I know that I did this in the past. And thus, these spots under the headstock that do not come in contact with the headstock itself, I actually safely can know that those will have no wear at all. And thus, I can use those as a relative measuring point to determine the wear of the rest of the things. Because I know that at one point, everything was square and parallel to the plane through this small patch that hasn't had any wear. And because that's hidden by the headstock, so it's not even like it could get bumped or scratched. It would be, that could sit there for 100 years, and other than maybe a little bit of surface rust, that would be the original plane. And so then I could actually do absolute, well, relative, but like measurements to determine actually what has happened over the use of the machine, and that could affect the way that I use it, or the way that I model the wear, the way that I do things, right? So, anyways, that's why the flatness of this matters. Now, it's important to note that we are going to an extreme level that you would not be able to get, right? You would not be able to, maybe you could personally commission someone out to do this, and you could literally be like, I want the most precise 10EE on the planet. I know you're really good at scraping and metrology. I'm gonna have you do it. And you're probably looking at like 6 to 12 months of work at machinist costs. You're probably looking at hundreds of thousands of dollars. Because if I were to take this lathe and I were to send it to a grinding shop to have them grind it down, basically send it somewhere that does lathe bed regrinding, which is a thing you can find probably 4 or 5 shops for in every state that like specialize in restoring lathe beds to a reasonable quality. They're not gonna do this. And I don't even think they would agree to doing this if I described it, because they'd be like, that's so out of the scope of our normal operations that we can't give you a price. We can't quote that. Like it's gonna be one massive project. It's just, we're doing it. So as part of that, I need really good measurements of these planes. Now, what I normally do, and the way that I've mostly scraped this, and I've been doing like rough scraping and I'm kind of experimenting with different scraping strategies. So the finish on here is not great, but it's not supposed to be. I'm trying to get through as much material as possible to get this where it needs to be. Okay? So, basically, what I normally do is I take a straight edge and I lay it across here with a bunch of blue ink on it. And when you rub that known flat straight edge across the surface, the high spots of the surface will pick up the ink, but only the high spots. Now, obviously, things will smear and smudge, but you kind of get this pattern where you know where it's making contact with the straight edge. And that is giving you information about where the high points are. And then you go in here with a scraper, which is this tool right here, and you literally go and you cut those spots off, and you just try and cut off the high points, and now that'll expose new high points that it will rest on. And you go through that process over and over and over and over and over again, and eventually you will try and get 2 surfaces into agreement with each other. Now, getting 2 surfaces in agreement with each other is hard when you have a straight edge that isn't as long as that surface. Because in theory, I can put a big like bow on the surface, and that straight edge will sit relatively tangent kind of across the entire thing as I move it, and I get this inaccurate reading where basically everything is being marked. But if I had one big straight edge, if I had one big straight edge, it would say that these corner parts are so low and there's no contact there, and the blue would only be in the center, right? And that's the hard part of kind of doing this work. So I'm trying to find different ways that I can measure beyond just that. So normally you can do that by feel. You can do it with where it hinges, but once again, that's by feel. It's very subjective. And given that doing one pass of scraping here probably takes about an hour, it really sucks when you spend an hour tackling measurements that are bad, right? If you spend an hour just continuing applying a curve to your curved surface, you're just literally wasting time. So the most important aspect of this is understanding the surface. Obviously with smaller things, most of these processes, even though they have those curves, they still kind of converge because your subjective feels do usually converge to something that's accurate. But for small pieces, that's normally okay. And also, I've noticed from some of my other scraping projects where I've scraped things that are like square or round or like rectangular but relatively wide, these ways that are very narrow and long, it's very hard to get a feel for your contact, especially because you could have a situation where this way is like angled up like a sawtooth, right? And you have this like triangle, and you're measuring the flatness of like this surface here, but you don't realize that you're like twisting this edge kind of the whole time. Or you could be putting a helix in here, right? Like a complex sort of curve where you're twisting things. And since it's a super narrow thing, you lose the ability to really notice that is happening. Whereas, like, basically, you want something that's long. The longer it is, the more bearing points, the more you have, like, the more it acts like a lever, I guess, I think is kind of what matters there. Because the narrow cross-section of that straight edge, there's really not much information. It's so easy to tip that straight edge, so it's kind of the wrong way, and you get a bad reading, once again, right? So, that leads to what have I actually been doing for the lathe, and that has been measuring level. So the only measurements that I have is the level of 2 points. So this is literally a level that just has a air bubble in it, and it's telling me what edge of the level is high and which edge is low. So this is an example of that's the preview image, so it looks like shit. Okay, thanks Discord. Open in browser, copy image, paste. Okay, so this is the level that I'm using, and this is sitting on this little dumbbell-shaped bar that I've made. So let me go and take a photo of that. So open the original. Open. There we go. Okay. So this is basically what I've made for all of my measurements. And this is effectively a dumbbell. And the reason that it's in this dumbbell shape is because this is a raised inverted V here, right? And thus this sits above this flat surface. And I can't put a straight edge across here because of that, right? I need a straight edge that's on stilts, right? Otherwise, it would bump into that. So, luckily, it's very common in machinist shops, and thus in my shop, to have these, which are called V blocks, right? And this is basically a block of hardened steel that looks like this, roughly, right? This allows you to set a circular piece of material in that V block, right? That's all it's for. It's just for setting a circular piece of material in there. Now, these V blocks are a matched set of V blocks, and they're brand new. So these are very nice, and when I say a matched set of V blocks, that means that they have been ground together, which means that literally these two V blocks would be fixtured together at the same time, and the grinding wheel would be run across both of them while making the surfaces. And the reason for that is that the machine has flaws and runouts and slopes and whatever. So you want to make these two things at the same time such that the fixturing has the same error for both of them. The grinding wheel has the same error for both of them, such that you're trying to get two pieces that agree with each other. They're also extremely square and parallel. These are, I think, are within 1/10,000th of an inch, so about 2 or 3 micron, I think, square and parallel. Could be wrong. Nevertheless, it doesn't actually matter what specification they're built to. That's really just what the manufacturer is willing to reliably produce these at. I specifically have gone through my V-blocks and my precision round stock that I have, and I have looked for the roundest, straightest, flattest, squarest, parallelest stuff I have. Which means that when I set these two V-blocks with this bar onto my surface plate here, this is a surface plate that is calibrated to like a micron or two of like deviation across basically the entire surface. So this is the reference surface for my garage. Basically, I can take this, set it on the surface plate, and then run an indicator across it, and I can't measure more than like 1 or 2 micron anywhere. So that means that basically there's 1 or 2 micron of error in this setup in being parallel to the surface below it. And that's all I care about, because I am setting my level on top of this round bar. And thus, what I'm trying to get is I'm trying to transfer information about the contact, the rectangular square, or the rectangular contact patch of underneath this block and underneath this block. And I am trying to directly transfer that information up top to the level. So it doesn't even matter that this is necessarily square and parallel, because the measurements that we're doing are actually relative, which is interesting. But once again, the more things that are square and parallel and indicate cleanly means it's more convenient to throw indicators on it and know and expect what you're going to get. Right? It's hard to measure things when you don't know what you're supposed to be measuring. So this is the little dumbbell that I built. So effectively, I treat this as a parallel, where this the top part of the bar is parallel to the bottom part of these flat surfaces, and that these flat surfaces are in the same plane as each other because I set this whole thing up on the surface plate, right? So I set these two things down on the surface plate, put the bar in, and then clamp the bar in very, very lightly, because I actually can notice from these bolts being tightened and clamping this bar down, which is just so the bar literally doesn't slip out and fall on the floor and drop everything around, clamping this bar down measurably affects the contact pattern between the points on the bottom and the top, right? Because it is pulling unevenly on the bar and basically flexing this material into the bar, which is based on the internal structure, right? There's, at the level that we're working with, every single thing is measurable, right? So, yeah. Wolf the Great asks, would you calculate the stresses and how much the bed would bend under the load of the spindle and rear headstocks and apron in SolidWorks to compensate for it during scraping? No. What you do, so basically I get everything flat and parallel, and then I'll set the headstock in. I'll measure how the headstock is running with respect to the bed, and then I'll take the headstock off, and I'll scrape the headstock underneath the headstock, right? So the bed and everything will always be parallel. It is the contact feet of the headstock that will be changed, which makes sense because that is a very fine-tuning thing. You want to have just your small contact points that you're adjusting. You can't change the plane of the bed constantly to like make those things work. Well, also it's just another fixture that you're attaching. So, but no, you don't have to compensate for that because your measurements include those bends, right? You can't scrape it into the unbent thing because your measurements include the bend, right? Because you have to put the headstock on to get that measurement. In theory, you could build a surface plate setup to scrape the spindle parallel to the base of the headstock, such that then you would expect to just lay the headstock directly on a flat thing and they would be in the same plane. But that requires basically building a lathe as your measurement setup. So like that, it makes no sense, if that makes sense. Nevertheless, everything on this is built so strongly that it will not curve under the headstock. It wouldn't even bend a micron. Even though the headstock weighs hundreds of pounds, the bed is so solid on this lathe that it would not deflect. Okay, anyway, so this is the little dumbbell that I built, and then what I do is I take the dumbbell and I set the level on top of it. You can see that I've denoted the left and right of the dumbbell and of the level. This makes sure that even if there is slope in the dumbbell, let's say this side was lower than the other and this is like always sloping down, that the way that I'm setting my level on there and the way that I'm getting these measurements means that that doesn't matter, right? And in metrology, you're effectively always looking for things that are relative or cancel each other out or converge to being correct. And this is a fantastic situation where the parallelism of this dumbbell doesn't actually matter. Obviously, it matters because my level is so precise that it's important that these things are flat and reproducible when I set this on slightly different positions. But in reality, we're factoring out one of the largest errors that could happen, which is a difference between these two blocks in their entirety. Really, the variance we're going to have is just where we set this on this round bar, which is effectively none. I can go through and repeat the measurements that I'm taking over and over and over again. And that's typically what I'll do is I will go and I'll take a whole set of measurements and then I will go and randomly pick out some points to remeasure to make sure that they measure to the measurements that I took. And that means that heat hasn't gotten into things haven't warped, I didn't bump something. It ensures that hopefully the measurements were taken from the same consistent environment during the entire duration that measurements were occurring. Because these measurements take like an hour or so, and thus the time of which it takes to take the measurements themselves can be enough time for things to change. Maybe I went to go get some food and I came back down to the shop and I set something on the lathe and I threw it slightly out of level, or I bumped something, or I got distracted, or I set something down and I got a chip under my level. Hopefully, the way that I go through these processes can detect that the readings are inaccurate and should be discarded. Nevertheless, the readings that I have been getting have been extremely consistent, really good, which shows that I think the way that I'm taking the measurements is either I'm doing it very well, or the way that I've designed these measurements have made them easy to take, which is kind of maybe what I would consider more important. Obviously, there's a skill cap to everything, but we want to make it as easy as possible to take good measurements. And that is the feel that I'm getting from these level measurements that I'm taking compared to the measurements that I get with the straight edge. With the straight edge, I am really not confident, and that could be a skill issue. That's maybe because I am not necessarily good enough at taking those measurements and knowing those feels. But what not a better time to learn how the straight edge feels against another completely separate form of measurement. If the two agree, if my mental model of how the straight edge feels and how this produces results, if they agree, then I'm very confident in both of them. But I think I trust the level measurements the most because they are extremely repeatable, extremely consistent, and there is very little human involvement in taking these measurements. Okay, so this is basically the level setup in here, and there's a small vial in here, and you can see the bubble. So there's kind of the end of the bubble, and there's the bubble here. So it's a really large bubble, and then there's these markings on here, the divisions. If you can see these, there's basically 3 on each side of a center line for measuring the level. So if you've ever used a level before, you'll be familiar with lines like this. Anyways, these lines, a singular one of these lines corresponds to this, 0.05 millimeters per meter, right? So 50 micron per meter is what this is measuring per division. So that effectively means that if I had a perfectly flat straight edge and I were to have this resting on a surface, and then this surface is on the same surface except I add a 50 micrometer, coin under there, and this is a 1 meter long bar, and then I set the level on top of this, this would read the bubble 1 division over, right? So that is quite sensitive if you think about what that is in degrees, 50 micron in an entire meter, right? Do you get the same measurement when flipping the dumbbell around? Yes, that's actually how you calibrate levels. And that's another reason why levels are fantastic, is you don't need a level surface to calibrate a level. Because you take a level, you set it down on a flat surface. It is important that you can reproduce the flatness, obviously, of the surface. You take the level, you set it down, and then you rotate it 180 degrees, and you set it exactly down on the same footing it had, and you want it to read the exact same reading. And if it reads the same reading, then that means that everything in the stack up is level and parallel and adjusted, right? And that's the really cool thing about levels. So like this level here has 2 little set screws in there to adjust, basically little set screws that push on the vial and will adjust the twist in the vial as well as the elevation of the vial. So right before I do any of these measurements, I'm calibrating that level against my surface plate. My surface plate is level enough that this always reads like within a couple divisions. Obviously, the level is most accurate when near the center of the divisions. So you want your reference, when you're calibrating your level, you want your reference surface to be as close to level as possible so that you aren't reading something like off the charts here, obviously, right? So, that is basically the level setup. So this is 50 micron per meter. And in this situation, we are measuring over a shorter distance. This is effectively, it's effectively like 25 centimeters. So since we are only bearing on these feet at this distance, we're actually we're measuring more accurately than that 50 micron. We're measuring, let's say this was 20, like the actual body of the level is 20 centimeters. Thus, if you were to just set that level on something, since this is measuring a ratio, well, your denominator here is not a meter. It is a fifth of a meter, 20 centimeters. And thus, you can actually just take that number, divide it by 5, and it's about 10 micron. So if you set this level down, and thus, since this dumbbell setup is only slightly larger than the level, effectively, 1 division on the bubble will correspond to approximately like 10 micron, right? So I can notice if this is up 10 micron higher, that's going to be roughly 1 whole division. Now, since this is an analog thing, 1 division is actually quite large. 1 division here is probably like 2 or 3 millimeters of deflection of the bubble. I can pretty accurately, by eye, notice half of a division. That is what I have decided I am comfortable taking these measurements as. I look at the bubble, and I take a reading that is to the nearest 0.5. So if I feel like it's mainly splitting between 2, I'll call it 0.5. If it's closer more to a line, I'll call it that line. Obviously, that means that the error in my readings are approximately 5 micron, which is fantastic. Because I know that this lathe is not flat to 5 micron. That would be basically factory spec. So that means that with this process, I should be able to accurately and consistently measure things to basically the factory specifications. In reality, since this lathe is 80 years old, it has significant wear, and thus we are still in the like 50 micron level, and thus I would say we probably have approximately 10x more precision than what we're measuring. So it should mean that we should be able to form a relatively good image of the bed of this lathe with this current instrumentation. And the goal is going to be to go from this level to the next level when I've earned it. Okay, chat? And that next level is this. This is the next level. That when I have proven that I am doing good things with level readings, once I have proven that, this is my reward, which is this level. I'll be right back. Okay, so, basically the goal of this stream and this project is to earn this level. Now, obviously, I'm not going to do that today. So, the level that I have right now is 50 micron per meter is its sensitivities. Now, obviously, I can read about 2x that, so I can read probably half of a division here because it's an analog device. In theory, there's more information there. This level that I want to get is a two-dimensional level that measures 1 micron per meter. So this level is 50 times more sensitive. This level is capable of calibrating surface plates. So that reference surface that I use to like build and stack up all of the stuff that I'm actually using to take the measurements that I'm doing right now, I could actually improve that surface with this. In fact, significantly. This is absurd. Because if you think about 1 micron per meter, I can make an arbitrarily sized base for this. So this has 3 sintered carbide feet for the base that are lapped flat. That's a really common thing. Obviously, when you're making precision instruments, you want them to rest on 3 feet, not 4 feet, because that means you are guaranteed to have those 3 bearing points with a flat plane. So if I were to build a little setup for it here, like just, make it maybe 10 centimeters, so I could measure like 10 centimeters out on each side, I'm actually getting 100 nanometers. I am able to detect a bump that is 100 nanometers tall, which is ridiculous, right? And since it's a level, this is also a 2-axis level, so you can do that in 2 axes in the same time. So the intent is going to be to improve my lathe to the maximum of my ability right now, which makes sure that I am emotionally commit to this project, because I don't want to spend money on a nice level and then not be good enough to use it, right? I need to max out my current capabilities before I can upgrade. Okay, so, does that make sense? Is a Lotus engineered to the same precision? No. I've seen how many shims are under that. You need to level up. So the level I already have, this is already a fantastic level. This level, I think, costs $12,000. $13,000. If you drop it, you send it back to the factory. I'm sure they would gladly recalibrate it for you and fix it. But yeah, so 3 sintered carbide inserts that are threaded on the bottom. So these are the center to center distance here. This site will have a better. So the dimensions of this thing is tiny, right? Which is good because once again, that allows us to amplify stuff. So 102 millimeters center to center there, and 85 millimeters center to center there. So just naked without anything attached to these feet, right? And you see like this instrument here, you could see how this would be really useful. As long as this sets really cleanly on the feet, I can now measure like twist, and I can measure on both axes of my lathe bed as I go down, right? So this would be just phenomenal to have. And having both axes measured at the same time eliminates another setup error in that you are taking 2 measurements from the same setup. So whatever errors are in your setup, at least both your horizontal and vertical measurements are from that same setup. So what's the technology behind it? I'm not sure. But its specs are nuts. So yeah, those are going to be sintered feet, sintered carbide that will probably be lapped, I would imagine. I'm not 100% sure. They're probably lapped. So yeah, it's let's see. What are the specs? Yeah, so the specs, 1 micron per meter, measuring range of plus minus 20 millimeters per meter, which that is also incredible. For reference, the level I have, since it's, yeah, that's 20 millimeters a meter. So mine is 0.05 millimeters a meter, and I have only like 6 readable divisions, right? So I can maybe go to like 0.3 millimeters, and this can go to 20, and that might not sound like a big deal, but that's so important for getting things initially level. Basically, you can probably eyeball something to 20 millimeters per meter very quickly. I can't use this level. This level effectively needs to be bootstrapped, right? This level needs to be bootstrapped by another level because this level is going to read out of bounds unless the thing is already very close to level, if that makes sense, right? So having that 20 millimeters per meter, even though that's still quite level, you could probably just ballpark. You can start using this level way earlier in the process, which is convenience, right? It's just more speed, especially when you have complex fixturing for a level like this that you can't transplant to your bootstrapping level. So it's important to have these things. How long do surface plates stay level once calibrated? So stay flat. It's important to note level and flat are different. Level is tangency to gravity, right? Whereas flat is just flatness in any plane. Thus, what I had to do is I had to put my lathe on 3 feet. Already had 3 feet. Obviously, that's how you want to hold any machinery, is 3 feet. The lathe had to be leveled very close to that. And when I take these different measurements, it's important that they're relative because just what we're measuring here is this level, even though I want that more improved level, this is already an insane level. A lot of machine shops would maybe not even have a level at this precision. They'd have like a standard like Starrett level, which is fantastic. This is more in the realm of like serious metrology level stuff already. With this level, my lathe will go out of level in probably a couple of months out of readings of this. That's not the lathe changing. That is like the concrete floor and gravitational effects locally changing, right? Like think about it though. Like this is sensitive, right? Under the 20 centimeter base of this level is sensitive to 10 micrometers across the base, right? So if this gets 10 micrometers higher, it will move one division. Now, think about how crude a concrete floor is, right? If a crack forms in your concrete floor, one side probably got higher than the other, right? Like there's some stresses, and this probably shifted up and this shifted down, right? That's a perceivable amount. That's enough to trip on. That's enough to like stub your toe, right? Your concrete, your foundation, your house, the dirt is moving way more than 10 micron, right? It's reasonable that you could have on a crazy winter an inch of move. Now, obviously, that's, normally going to be sheer in like specific areas and whatever, but it is completely reasonable that this will move enough that I couldn't go out here, take one set of readings, then go out there in a week and take the same set of readings, because just everything will shift. It'll be a different temperature. It's really cool to work at this level of precision because it requires really being humble, because you can't assume you know what's going on. Like someone who's really hard-headed and comes in here and like sets their mental model, they're probably not capable of really doing metrology stuff, because you have to be comfortable with the fact that like you are never going to measure things accurately. You can try and collect as many measurements as possible to decrease your error, but we're talking at the level where like temperature and local like earth shifting is affecting the measurements. And thus it makes it a really fun problem where you just have to constantly remeasure and just be critical about what you're doing. Which I think is really healthy and fun. Okay. So anyways, what I'm trying to do is I have that dumbbell set up, and then I take that dumbbell and I run it down right now every 40 millimeters, right? Every 4 centimeters. So what I've done is I've taken a tape measure down the lathe bed. I've marked a line at every 40 millimeters, right? And you can see that on both sides. And these I try to line up as close as possible, but it doesn't really matter if they're not perfect, because if this sets a little bit at a diagonal, as long as it's consistently diagonal, it's the same information, right? So even though this is kind of eyeball-y, whatever. Then what I do is I pick an edge that I want to be like the reference surface on the dumbbell, and I'll take that and I'll slide it across, and usually I'll take a photo. So this photo is actually one of those photos. This is a photo that's basically a reminder to me of how did I take these measurements. And in this case, I see that there's 40 millimeters between these, and I see that the back side, the left side, is the surface that I'm lining up with the line. So what I'll do is I'll measure with that line. I'll then advance this dumbbell. I'll then measure with that spot here. And I'll advance the dumbbell again and measure it at that spot there. And what's cool is that this is wider than 40 millimeters. So there's actually some super sampling going on there. We're sampling. We have probably basically 2 data points that rest across everything here. So if we do have some error, there will be some averaging, because some spots won't pick up that error and whatever. The thing is, it's really hard to interpret this information. So basically, I run that down the bed. I do the same thing across that bed. Once again, the level is always in the same orientation, right? The left and the right and the left and the right line up here. And I'm always going left to right down the lathe bed. Now, it's important to note that the front of the lathe is actually here. But for modeling reasons, and just the way that I physically get around the lathe when working on it, when repairing it, this is the front of the lathe to me in software right now. And it's easy to tell which is which because one of the beds is longer, right? This is the longer bed. So, for reference, this is like where the camera is facing in our software, right? Because here's the long side of the lathe bed. And in this situation, oops. The long side of the lathe bed is at this far right corner. Will always going left to right cause a bias of any sorts? No. In absolute terms, yes. But since we're only caring about the relative measurements, I'm actually making sure that I'm measuring in the same way, such that if this was a wedge, right, let's imagine that this whole like level setup is on this massive wedge, that the wedge is facing the same direction for all the measurements, right? Now, that doesn't mean that what I'm measuring is level, but it means that I am, if this dips down... Did my computer shut off again? Did it die? Am I still here? Yeah, I'm still here. Okay. I think that was just Twitch just on my ingest. Okay, anyways. So yeah, the reason that we're doing this is where I'm saying that we are trying to find a way to fundamentally eliminate variables. And this is a good way, right? Let's imagine that this dumbbell is this kind of shape. And I don't know if these drawings, when I'm drawing them in 3 dimensions, works at all. But effectively, if we said this whole dumbbell setup had this shape, and we put the level on top, and then we level the lathe with respect to that, such that the bubble reads at 0, if I move this whole setup down, and then the bubble moves one marking over, right? Then I know that this raised or lowered relative, right? So it doesn't matter that there's error, parallelism issue in my actual setup, and that is a variable that we've eliminated. The precision of basically the rod and all of these things doesn't matter, or specifically just the heights in this case, because the flatness of these bottoms matter, because we're relying on the flatness communicating the surface contact with the bed of the lathe. But the stack up above, and I have another bubble here that's not a super accurate level, but I use that to make sure that the level is level in this dimension, such that we're sitting basically flat up and down on the bar, and we're not twisting the level, right? We don't have the level laying down on the other bed when we take the measurement, right? So, all of those things kind of cancel out a lot of the errors that we have. Really what I'm looking for, I think, is the concentricity and the flatness of the top bar is important, because in theory, the level isn't always going to get set on top of the bar at the same spot. It might slide backwards and forwards a little bit, and thus if the bar is off, that would affect things. But that's really it. Since the bar is rigidly clamped to the V blocks, that is a rigid setup, so that is all accounted for. And I've been able to rub the dumbbell on the surface plate to pick up the marking of where the dumbbell makes contact with the surface plate, to guarantee that I know that the 2 planes of the bottom surface or the 2 V blocks are in the exact same plane. Right? So I know that the bottom of this is perfectly flat. I know that the bar on my surface plate doesn't indicate more than like 1 micron of deviation across the entire spot, which also means that it's parallel. But the parallelism doesn't matter anyways. That's kind of all of the measurements there. And then there's one other measurement that we take. And the reason taking these measurements is not linking the two beds together, right? So these two beds could both be flat, but they could be in a completely different plane. They could be angled away from each other. They could, all sorts of issues, right? So now, what I also do is I have another pass where I go horizontally across the two, which is the whole point of the dumbbell setup compared to the other setup. And it's this measurement. Same sort of thing. This I'm using, I think the back or the front. I can't remember. And I'm probably the front because I start off here. And I basically move the level down and I do the same thing. And now I'm getting readings across these 2 points, across the planes. So now, if these were both perfectly flat, but they're not in the same plane, they would eventually start to deviate here. Because one would be going up and the other would be going down with respect to each other, right? If that makes sense. Okay. So what I do is I go and I take all of those measurements. And the way that I take the measurements is in bubbles. So I read the level, the way that I read the level, and there's a bunch of ways that you can do these things. Let me rotate this. How do you rotate? Image, transform, rotate, counterclockwise. Okay. So the way that I read this level is, since this bubble, basically I only read the right side of the bubble, and I treat this as the left side of the level, this is the right side of the level. The reason I call that left and right is because this is the way that you read the font, right? So that's the left and the right side of the level. I read only on the right side of the level. And I read where the bubble is. So in this situation, the bubble is kind of like halfway between these lines. So this is negative 0.5, right? So that is what I call negative 0.5. I completely ignore this side of the level, right? I'm just reading the right side. Once again, these are relative measurements. So all I need to make sure is I'm doing the same thing every time, right? If I were to read a little bit on the right side, a little bit on the left side, then the size of the bubble affects some things as well, right? So this would be like a negative 0.5. Then I go and I take all of those readings and I just write them down in Sharpie right on the lathe bed. So here you can see I was writing them down as I go throughout the bed, and then the same thing here. Then, that's it. That now tells me what's going on. So, in this case, let's say this is a negative 0.5. Negative 0.5 in this case is half of this. So it is 25 micron per meter is what the angle is, right? That is a slope. That is an angle reading. It's not reading anything else. So that angle now needs to be relative to this contact patch and this contact patch. So let's just say, for simplicity, that this is 10 centimeters, 100 millimeters, right? Then this would be, instead of 25, it'd be 2.5 micron. And since it's negative 0.5, that means the bubble went this way, which means this side is high by 2.5 micrometers, right? So effectively, a negative reading means that the left side is high, and a positive reading means that the right side is high, right? And this reading is just an arbitrary way that I've decided to quantify what I'm seeing here, right? And I just go through, try and keep my head, as flat as possible. I try and get the best reading. Once again, you're eyeballing it. That's why I'm only doing like rounding to a half. It's hard to really go beyond that. I think I could maybe do a quarter. Once everything's like really level and it's not moving around that much, then I probably could go and start splitting hairs and trying to pick out quarters. But that is basically the system that I have set up. So then I've taken all of those measurements, and those measurements are here, right? So I have the across data, I have the long, the slopes for the long way, which is just the way that is longer than the other, and the data for the short way, and there's more for the long because there's more readings for that. So this is the information I have now. So luckily, unlike when I originally started this lathe project, everything is actually within readings now, within tolerance. Previously, the first time I did these measurements, I had readings of like -6. And if you can imagine, -6 is like off the chart here, which is really me eyeballing like 6 in here on the left side, which is, you're not supposed to read out of bounds of things. But once again, this level was too sensitive for the wear of the lathe, right? This level would deflect and change more than the lathe. Like, the lathe had more wear than this level could accurately measure. Anyways, so all of the information is, all of the data is now within that. We have a 2.5. That's our worst. On the actual slopes, our worst is like a -2, but really what matters here, what's interesting, is on the slopes, it doesn't matter. What matters is the relative difference between these. If every single one of these slopes read at -2, then it's flat. Right? Because that means that all of the readings were the same level. Now, it means that the machine is not out of level, but if we adjusted the machine, then every reading would be 0. Right? If that makes sense. So, to me, it is very, 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 very difficult to interpret this data well. So, that's why I'm writing software to do it. And the goal of this software is not to do like AI hill climbing to converge to a shape. Instead, I want to do fuzzing. And that's not just a quote because I only know how to do fuzzing and I'm a one-trick pony. The reason is, what I want to do is I want to observe what is tolerable for large amounts of variance in the randomness. So I want to basically have a live view of trying different surfaces, because the surfaces that it's trying will tell me if there's any measurements that are missing, right? If there is unconstrained, unmeasured surface, right? If there is surface or a measurement that is not relevant to the data can just go random, right? It could be 1,000,000 feet tall, right? Like, if I had these measurements here, right, and I skipped a 1-foot region where the level never made contact, the feet of the level never made contact under those two patches, my software will hopefully lead to like massive pits and valleys and noise and chaos in there, which effectively is signal to me that I need more measurements. Effectively, there is not enough information for it to constrain that. Now, since we're measuring wishy-washy data, we don't have true data, so we can't mathematically solve, right? Because this isn't a modelable surface. So we can't differentially do this. Now, we could make a simplified model and then do like AI ML, but that's going to converge to something. And that's going to be hard to see those fluttery, fucky areas that are super unconstrained, right? Now, obviously, you could still see those a little bit. But Blaze Bits, thank you so much for the raid. Hell yeah. Is that a cookie monster? Hell yeah. How's it going? What are you up to? Do you have fun? So that leads to, how have I designed this software? And basically, what I want to do, and it's what I've written, okay? But what I'm trying to do is I am trying to model what I have built for measuring. So effectively, what I want to do is I want to randomize the lathe bed, but assume the properties and behaviors of my measuring equipment, and then I randomly generate a bed, and then I simulate where that measurement, where this would sit on the bed, and thus what the measurement would be, and then I can optimize for that error. And the great thing about that is I don't have to think about, like, what are the pitfalls of these measurements? Are there weird things that lead to measurements not mattering, or weird things that lead to a twist, even though there isn't a twist, but it's misleading because something is going up while the other thing's going down, and it's just like a complex two-dimensional twist that is really hard to, like, understand, right? So I don't want to try to communicate with software what the surface could look like. I just want to say, these are the measurements that I'm taking, randomly generate surfaces, run the measurements on those, and tell me what happens. We're building an Active Directory hacking lab. Hell yeah, how does that work? Do you, like, set up like a large Active Directory, like, setup? And then, like, is it for, like, network propagation? Or, like, looking for permission issues? I don't even know necessarily what Active Directory hacking ends up being. Lots of fun, but this lathe testing you're doing is crazy interesting. Yeah, this is just what I do. Like, this is what I do in fuzzing. Like, to me, working in the garage is no different in terms of difficulty, complexity, all those things. It's really cool to, like, try and go deep on these things and understand them. So anyways, what software are you in? This was GIMP. Yeah, this is GIMP. So anyways, this is the information that I have taken, right? This is the across data, which is based on that, like, bubble reading that I talked about, which is how I take my data. So the across data, long and short data. And then I've kind of done some ASCII art to describe the geometry of the tools that I've built. This is basically saying that these are 62.01 millimeters wide. They're 62.2 millimeters long. These, like, the individual V blocks. And then the start and the end is 273.16. So from that, I can derive all of the 4 points of these. And then I assume that this bar doesn't exist. Right, I'm not doing a physics simulation here, so it doesn't need to know that something exists at a higher height. I'm just simulating these two bottom contact patches here. Okay? So, and then what I have done is I've written an algorithm for what I call hatting. And hatting probably has a real term, but I don't know what it is. And effectively, what hatting is I try to find the 3 points of which a perfect plane, so a perfectly flat software plane, sets on 3 points with the lowest amount of error, right? So, and the algorithm that I have designed to do that is exactly what you would think. I go through every single combination of all 3 points, and I then go through every single point, and I compute the error to the plane that intersects those 3 points. If any of those points go above the plane is eliminated, because the plane could not rest on top of that surface because there's a point that would pierce through the plane, right? So I am looking for a plane that rests on top of the rests on top of the surface on 3 bearing points and has the lowest error. That is what I am basically saying is happening in real life, is I am setting a perfectly flat plane, flat with respect to my surface plate, which is a very flat reference. Once again, we're assuming that that's perfectly flat. We take that, and we're setting it down, and that is determining the contact patch across those 2 ways, and thus the reading that will go into the level, right? So I am trying to basically find where those 3 points would lie for that surface to sit. Now, there are always multiple solutions to that, and this is like an n to the 4th power algorithm, right? This is a catastrophically slow algorithm. But I don't actually know if there is a simplification for this algorithm that is correct. It's fascinating. Now, there are algorithmic improvements that I can make to implementing this strategy, right? Through like caching and there's just a bunch of like differential computing stuff that I can do to improve the performance of the design of the algorithm, right? Which is more like micro optimizations that can be made to this. However, I don't know if there is an algorithm that is better than, for each combination of 3 points, find the plane. Or try every point, see if they intersect, and if they do, then you have to eliminate it, because it doesn't sit on top. Anyways, gradient descent will find a local minimum. It won't find a global minimum. I'm looking for a global minimum. So, effectively, like, gradient descent is effectively going to just end up making a 2D regression and then move that to the top of the surface, right? And that's what I originally did, but it's actually just not accurate to how things rest, right? Because you can just have a random high spot, and yeah, it can really fuck things up. And there's really difficult, I don't know, it's just weirdly a hard problem. I've put a lot of thought into it, and it's just weirdly a hard problem. For something you would think would have, like, a solution that, like, magically works, I genuinely don't think there's anything better than the, like, end of the 4th. Which is crazy. Now, mine has, like, pretty good best case performances. It's probably more like n cubed or something in its actual runtime. But it's a hard problem. Okay. So, let me try and show you the software. So, I just wrote kind of a new surface randomizer that's really cool to try out. So, let me show you how the software works. So, assuming there aren't bugs, but I don't think there are. Okay. So, what I'm going to do is I'm going to create a surface. Here we go. So, we'll make a surface. We're going to say it's 64 by 64 millimeters. Right, so I'll say a 64 by 64 millimeter surface. And then I'll adjust where the camera sits, so it will be visible 32 and 32. And then let's do surface dot randomize, okay? Oh, and then this needs to take a area to randomize. 64, 64. I think that. Okay. Surface selection. And surface. Oh. Sorry. Ref surface draw hats. Let's just get rid of hats for now. And then, oop. I have like a bunch of feedback stuff in here that I'm playing around with. Anyways, so this should be generating random surfaces. And yeah, so I can amplify the amount of randomization and the strength of the randomization. Let's just amplify the strength just so it's a little bit more obvious, right? So this is generating just effectively random surfaces, right? And then let me actually switch my code. I have code that this surface dot recenter. Okay, fn randomize, fn recenter, mute self. So this is going to move the average height of a point in the map to 0. This recenters the map. This is just useful for visualizing, right? And this is gonna find the average point depth, and then this is move the average to 0. Right? So that's just moving the plane. Because my random will cause it to kind of go crazy a little bit. And I like to keep the numbers as small as possible. Surface dot recenter. Okay. Yep. So that's staying nice and centered now. Okay. So this is just generating a bunch of random surfaces. And then what I can do is I can build hats. And I have a hatting function. Hats. How do I do it? There we go. So then on that surface, I can hat. And this takes a range of things, I think, like this. 0 dot, 0 dot, 4 dot, 4 dot. And then I should be able to hat dot draw here. Something like this. Hat dot draw. Oh. Because this gives me a perfect plane, and then I say where I want to project that plane.